My name is Jamie Alegel Girolona, and we're gonna talk about chemistry of water treatment. Introduction: Drinking water standards. Primary drinking water standards, secondary drinking water standards, other rules promulgated by EPA. Drinking water standards. A community water system is one that serves the same people year-round. Example, residences, homes, condominiums, and mobile home parks. A non-community water system serves the public but does not serve the same people on a year-round basis. A non-transient non-community water system is defined as one which serves the same people for 6 months but not year-round. Rest areas and campgrounds are considered transient non-community water system because they serve the public but do not serve the same individuals for more than 6 months. Introduction: As authorized by the Safe Drinking Water Act, the U.S. Environmental Protection Agency established drinking water standards for various contaminants, primary or secondary. Primary drinking water standards are established to ensure safe, finished water, include microbiological organisms, disinfection byproducts, organic chemicals, many of which are priority pollutants, inorganic chemicals, radionuclides, and turbidity. Secondary drinking water standards are not related to health and are therefore non-enforceable by the U.S. EPA. Secondary contaminants cause a variety of problems that can be categorized as aesthetic, cosmetic, and technical effects. Other rules promulgated by EPA. Groundwater Rule. Its purpose is to reduce disease incidence associated with microbial contaminants in drinking water, and it applies to all systems that use groundwater as a source of drinking water. Long-term 2 Enhanced Surface Water Treatment Rule. The LT2 rule is to reduce illness linked with the contaminant Cryptosporidium and other disease-causing microorganisms. Stage 2 Disinfectants and Disinfection by Products Rule focuses on public health protection by limiting exposure to disinfection by products, specifically total trihalomethanes and 5-haloacetic acids. Long-term 1 Enhanced Surface Water Treatment Rule. The purpose of this rule are to improve the control of microbial pathogens in drinking water, specifically the protozoan Cryptosporidium, and address risk trade-offs with disinfection by products. Filter Backwash Recycling Rule, a rule governing the process of recycling wash water from the backwashing of drinking water filters. Arsenic Rule. The rule requires monitoring for new systems and new drinking water sources, and also clarifies the procedures for compliance with MCLs established for inorganic contaminants, synthetic organic chemicals, and volatile organic chemicals. Stage 1 Disinfectants and Disinfection by Products Rule. Improve drinking water quality by providing protection from disinfection by products. Interim Enhanced Surface Water Treatment Rule. This improves the control of microbial contaminants, particularly Cryptosporidium, in drinking water systems serving 10,000 persons or more and that use surface or groundwater under the direct influence of surface water. Lead and Copper Rule. On June 7, 1992, US EPA published a regulation to control lead and copper in drinking water. The rule requires all community water systems and non-transient non-community water systems to comply with the rule. Total Coliform Rule. The rule establishes both MCLGs and MCLs for the presence of total coliform in drinking water. All public water systems must monitor for the presence of total coliforms in the distribution system at a frequency proportional to the number of people served. Surface Water Treatment Rule seeks to prevent waterborne diseases caused by viruses, Legionella, and Giardia lamilia. Overview of typical use for contaminant removal. The alkalinity of the water may be insufficient to resist a change in pH when certain coagulants or coagulant aids are added to the water. Generally, lime, caustic, or soda ash is added to the water to increase the alkalinity. Arsenic dissolved in water is found as arsenite or arsenate. Coagulants such as alum, ferric chloride, ferric sulfate, and lime have been successfully used to remove arsenic from water. Ferric sulfate coagulation at a pH from 6 to 8, alum coagulation at a pH from 6 to 7, and lime softening at a pH greater than 10.5 have been effective at removing arsenate. However, arsenic must be in the form of arsenate for coagulation to be effective. If in the form of arsenite, first it must be oxidized to arsenate by adding chlorine or permanganate. Barium can be removed effectively by lime softening. Greater than 90% removals have been achieved in the pH range of 10 to 11 on groundwater containing 7 to 8.5 mg per liter of barium. Kawamura indicates that barium can be removed either by lime softening at pH of 10 to 11 or by ion exchange with a sodium regenerate cycle. Laboratory and pilot scale studies have shown that greater than 98% removal of cadmium by lime softening can be achieved in the pH range of 8.5 to 11.3 for samples with an initial cadmium concentration of 0.3 mg per liter. Ferric sulfate and alum coagulation have also been used for cadmium removal, but their use is not as effective as lime softening. Chromium can be removed easily using alum or iron salts and by lime softening. Aluminum and iron salts or lime softening are not effective at removing hexavalent chromium. Ferrous sulfate first must be used to reduce hexavalent chromium to chromium for these coagulants to be effective. Color removal traditionally has been accomplished by oxidation with chlorine, chlorine dioxide, oxygen, or potassium permanganate. Granular activated carbon and powdered activated carbon can also be used for color removal. Coagulation of dissolved and colloidal species causing color may be accomplished with alum, coppers, or ferric salts. Fluoride. Fluoride can be removed during lime softening if the magnesium concentration is high, according to ASCE/AWWA. Alum coagulation at high dosages will remove fluoride, but it is not considered economical. Ion exchange with activated alumina or lime coagulation at pH of 9.5 to 11.3 is recommended by Kawamura. Gases. Dissolved gases that may be found in groundwater include hydrogen sulfide, carbon dioxide, methane, and volatile organic chemicals. Carbon dioxide is typically removed by air stripping. Diffused aeration is sometimes used instead of air stripping. Iron. Dissolved iron must be oxidized to ferric ion before it can be precipitated and removed by sedimentation and filtration. Oxygen, chlorine, ozone, chlorine dioxide, and potassium permanganate have all been used as the oxidizing agent. Lead. The stable solid phase of lead depends on the pH and alkalinity of the water. In water treatment principles and design, dissolved plumbic ion is the prevalent and stable lead form at low pH. Kawamura also indicates that lead can be removed by ferrous sulfate addition at a pH of 7 to 9, alum coagulation at a pH of 6 to 9, and lime softening at a pH of 9.5 to 11.3. Lead can be removed by coagulation and lime softening. Manganese. Manganese is the dissolved form like iron. It must be oxidized in order to be precipitated and removed from water. Mercury. Kawamura stated that inorganic mercury can be removed by coagulation with ferric sulfate at a pH of 7 to 8 and by lime softening at a pH greater than 11. Organic mercury in the form of methyl mercury ion is the more prevalent and toxic form with less than 40% removal with alum and iron coagulation. Granular and powdered activated carbons are effective at removing organic mercury from water. Nitrate. Nitrate is relatively unaffected by conventional treatment consisting of coagulation, flocculation, sedimentation. Ion exchange is the simplest and lowest cost method of removing nitrate from contaminated groundwater. pH. Often, the pH of the water must be adjusted by adding either an acid or base. Sulfuric acid and phosphoric acid can be added to lower the pH, whereas lime or caustic soda is added to raise the pH. Radionuclides. The principal source of natural radionuclides is uranium ore. In full-scale experiments, lime softening removes 70 to 95% of the influent radium concentration. The best available treatment for radium-222 is aeration, while combined radium-226 and radium-228 treatment consists of coagulation and flocculation. Taste and odor. Taste and odor compounds may be related to organic compounds, secretions from algae, and/or inorganic compounds. Activated carbon is the most effective means of removing these compounds, whereas chlorine oxidation is the least expensive method. Total organic carbon. Total organic carbon can be removed by lime softening and/or coagulation. However, coagulation is more effective than just using lime softening.